So all these process are repeated with the same technique only. Okay. Then in the then in the upcoming lithography part, the patterning a layer above silicon surface. Okay. So now how patterning a layer is done. So this is the technique of fabricating the polysilicon layer. The polysilicon deposition is done on the top of SiO2. So this is a substrate. On top of this one, let me show you. Okay, let me show you over the paint. Then it will be easy for you to understand. Okay, of the paint. Oh, 1 second. Let me show you to you over the paint. Then it will be easy for you to understand. Let me check whether our record on or not. Yes, recording is going on. Okay. So when we actually do, see, when actually there is a substrate, suppose, okay, this is a substrate. In this one, actually, this is the gate oxide. So this is the silicon dioxide. Okay. As you see in this one, so if you see in a substrate, this is the SiO2 layer. Okay. Same, this is the sub I am writing here. This is the SiO2, silicon dioxide layer. Okay. On the top of this one, a polysilicon material is provided. That's a kind of a material that's used for etching the polysilicon layer actually. Okay. So this on this top part, a layer a layer is being deposited on top of this one, which is responsible for polysilicon etching. Okay. So this afterwards it will be converted to polysilicon, that gate part, which is the connection of the gate connection. That green connection you have seen in that one layout, that green one you see long one, that is the polysilicon layer actually, poly layer, which you termed in the layout actually. Okay. If you see here in step one, the polysilicon is being deposited. Then in the top of that polysilicon, a photoresist material has been given. Like if you see here, let me show you to like this. Let me put a color here. Let consider this polysilicon as a green color. Okay. Let me consider this as a green color. 1 second. That part is empty actually. Let me connect it. Okay. Okay, so this is actually a polysilicon material given on top of this one. Okay, suppose this is the gate oxide. This one is the gate oxide actually. Okay, gate oxide, and below one is your sub part, sub actually P sub, or the substrate, what you can tell. Okay, or you can tell the substrate. Okay, in the top, this green color is the polysilicon layer. In this top of this polysilicon layer, what they will do, they will put a photoresist material. I am considering photoresist as a brown color material. Okay, let me draw one layer from this part. Then I will able to show you the polysilicon that material. Okay, I think that will be great to go. Let me do it here like this. Okay, I am doing it like this. Then on top of this one, we are putting again this kind of material. Okay, and then suppose this brown color is considered as a green one is your polysilicon layer. Okay, then in top of that one we are putting a photoresist material. Photoresist material you all know. So can anyone tell me what is the purpose of the photoresist material? I already told. What is the purpose of the photoresist material? What does it do? What does it does? Hello. Hello.
When we apply UV rays,
Mm-hmm.
it will be soft at that part only.
Yes, photoresist is a photosensitive material. Okay, if you have seen those kind of film which are used to use in the cameras, earlier camera, that camera reels, that black reels, that from Kodak it is supposed to come. You might have seen that reel. That reel has a photoresist coated material. When you used to click a picture, if you have seen that mechanism, now the digital cameras are there. That is also work on that kind of principle only, but that's a very basic thing. So if you see on that one, when the let me tell you that thing again. Suppose this is one guy standing here. Okay, this is one guy standing here. Okay, the guy standing here. Okay, and this is one photographer. Suppose he is clicking a photo actually. Okay, he is clicking a photo actually here. Okay, he's clicking a photo of this guy. What happened in this photographic camera? In this part, if you see here, in suppose in this part, suppose this is the lens actually, here is to be a shutter kind of thing was there. When the guy, the photographer used to click the switch from at this point, okay, the shutter used to open. The shutter used to open. Okay, so the shutter used to open in this part. Okay, and what happened? The light that suppose a shutter open for a 1 millisecond. Suppose the light till that time, whatever the light reflecting, the light is supposed coming from this direction. Okay, so this direction light is coming. Okay, so what happened? The lights come. This is obstruction. The whatever the light passing from this part, whatever the light passing after striking this guy, the some light will revert back actually. Okay, some light is going and striking this guy, then some light is reverting back, and some whatever the light is passing through this guy from his side, that will go and enter the camera actually, camera lens actually. Okay, and that camera lens, that light will go and strike that photoresistive material. That is the reason it was said that don't put those reels over the exposed sunlight or any 100-watt bulb, because that light, that film will get damaged, because that light will be capture on that one. So that is the photoresistive material actually. So on that one, that photoresistive material, you should track this guy's image on that one. So same concept is applied here also. Okay, so this photoresist material is put on this top of this one. When the UV light is now passed from this part, when suppose now the UV light is passed from this part, suppose we need a, suppose this is a UV light. Okay, so this is the mask what you have designed. Suppose what Ganesh, Nanda and Akila has designed a mask. Okay, so this mask was containing this level of structure. This polysilicon kind of structure cutout is there. Okay, this part is opaque. This is a opaque part. Other parts are opaque in this one. Okay, and this part is only responsible for passing the light. From here only you can pass the lights. Okay, let me color it with yellow color. Okay, sorry. So let me put a color here actually. I think that will be great to do. Let me put a color here. So okay, so I'm putting this is a blank space. It's a blank. Okay, it's a blank. Okay, actually. Okay, or one thing I can do here is let me color the side only. Okay, let me color the side part. Let me, what happened? Okay, let me color the side part. Okay, let me color the side part. So this part are actually opaque part. So light cannot pass from this area. The black areas, light cannot actually pass. Light will get stopped because this is the opaque part. Only from this part, that cutout part, only light will pass. If the light will pass, what will happen? If the light now passes from this part, if the light passes from this part, suppose, wow, what will happen? We will suppose the light is passing from this part. Okay, light is passing. So what will happen? The light will actually appear on this part. Okay, on this part the light will appear, and a structure same to same this kind of cutout will also get appear here. Okay, so also this kind of structure will again appear at this level. Okay, if you see this kind of structure, it will get appear on this level. Okay, now what happened? Now let me now, this part, this brown part is solid now. Due to falling of the light at this rectangular part, what happened? This part becomes softened. This part become now soft, due to which means the light has passed from this part and this part has become soft. This red one, it becomes soft, and the brown one is now hard. Now there will be etchant. The etching will be there, okay, using fluoric acid, hydrofluoric acid, or nitric acid. Etching will be there. When the etching will be there, the soft part will get out of this one, okay. The soft part will come out of this one, okay. When the soft part comes out of this part, the other part will also get removed. And now what will happen, if you see here, this kind of this material will be there. A photo silicon etching, the hard like top kind of structure will be on the top of this one, okay, will be on the top of this one, okay. Now what will happen, the everything will be structured. Now what thing I have told you, one wrong thing, the light which is passing, actually it will not pass in this level, okay, it will not pass in this level. Let me tell you, actually I did it one wrong thing by mistake. I got okay, you, it will not pass like this, okay. Only the thing will be there is, let me tell you, okay, then let me repeat again. Okay, this part will be opaque, not that part, okay. This part will be opaque, okay. This part will be opaque. This part will be only opaque part, okay. This part will be opaque, okay. And this part will be have a cutout. This part will have a cutout, actually, okay. Because the structure we need here is a bump out structure we'll need here. If you see this diagram, we need this kind of bump out structure in the center of this one. That is the reason we need a cutout in the sideways, not in the center. Actually, we don't want it in center, okay. So this will be the transparent part, these two sides. This will be the opaque part. Now when the light will fall from the top, actually the earlier one what I told, it was only applicable for NVEL and the metal process. So this is only applicable for the polysilicon process. Wherever what kind of structure is needed, that kind of mask will be designed, okay. So from here the light will now pass. Now light will start passing from here, actually. If you see, the light will start passing from here and here, okay. Light will pass like this, okay. Light will pass like this, but it will not able to pass because this is a opaque part. So this part, this two part is empty part. Now light will be falling on this light will fall on this top part, actually at this level. Actually at this level the light will fall, okay. The light will fall on this level, actually. Excuse me. And then, okay, now it is okay. Now it is okay. The light will fall on this level, and this level will be normal. This level, because the light is in falling at this level, light is falling only at this level, okay. Only at this level light is falling. If you see, the light is falling at this level only. At this level light is falling. Again, same for this guy also. But in the middle there is no light, because we want this to be structured out, okay. After this is done, this part will become softened. This part will get softened, actually. If you see here, this part will get softened, actually. These two both part will be softened, actually, here. Okay, 1 second. Please give me 1 second. Hello. Yeah, I am back. Okay, now what will happen? This two part becomes softened. Okay, this two part becomes softened. Okay, this red part become now soft. Now due to what's happening, now when we will etch this one with a hydrofluoric and nitric acid, this red part will be washed out. Okay, after it is get washed out, you will see a structure. I'm removing all these things. Okay, you will be seeing a structure kind of this, okay. Let me show you the structure. Actually, now the structure will come here is kind of this kind of structure will come. Let me show you the structure actually. The structure will come here as this kind of structure. This kind of structure will come on top of this one. Okay. On the top of this one, this kind of structure will come out. Let me clean it. This kind of structure will come out on top of this one. Then again, we will wash this. This every brown color thing will go out of this one. This brown color thing will go out of this one. And then you will able to see this kind of structure will come actually in this part. Okay. Now let me show you. Again, let me show you this part. Again, this kind of material will come out actually. Okay. Okay. Now this kind of material will come out on this top of this one. Okay. Now I have that made it as a black color as it is a silicon dioxide. So it should be a gray color actually. It should be a gray color actually. It should be a gray color actually. Okay. It should be a gray color. 1 second. Okay, now it should be a gray color actually. Now, if you see the silicon dioxide has came on the top of this one. If you see that one, the silicon dioxide has already came on the top of this one. And then the now structure will be like this. On top of this one, if you see the structure will be kind of like this structure will come out. Okay. This kind of a brief shape structure will come out on the top of this one. Okay. This is how actually the structure of the polysilicon gate looks like. If you see in that diagram also, you will get to know this kind of structure has came out on the top of this one. So this is how the polysilicon poly etching is done. So this is sorry, excuse me. So this is the process of poly etching completely. This kind of steps are repeated multiple times to make multiple shapes on top of this one. Okay. So do you guys want me to show you a video, a kind of PCB etching? Like, do you want to see a kind of practical, like I cannot show you the MOSFET thing, but I can show you a PCB etching. Do you guys want to see that one? Then I will able to show it to you. Hello.
Yes, sir.
I see MOSFET teaching I cannot show you, but I can show you the PCB fabrication. How PCB fabrication, you will get some couple of ideas. Okay, so rest other thing you have to read from the PDF. I will teach you, but the PCB etching when it will done, you will able to get a brief idea. I cannot show you live here. I will do it and I will send you a recording actually. Will it be fine? I will upload the recording.
Okay, sir.
Okay, I think it will be bit easier for you to understand the etching process. Okay, so this is how actually etching is normally done. So now comes the lithography of the other part. Like two kinds of etching is done. There are two kinds of etching: wet etching and dry etching, which is also called anisotropic etching and isotropic etching. Okay. Now, in etching process, what is etching actually? You should be knowing. Process of removing unprotected material. Unprotected means the way I told actually that green, that a part which is getting softened, we have to remove that one. That is the unprotected material. Wherever photoresist material is there, the mask is being top of opaque part that is protected. Other things are not protected actually. Okay. So process of removing unprotected material, etching occurs in all directions. Horizontal etching causes a undercut. Preferential etching is minimized to undercut. Okay, so there are some kinds of etching, horizontal, vertical, those have some kind of issues also. Okay, so if you see here, there are two kinds of etching techniques: wet etching and dry etching or plasma etching. Wet etching uses different kinds of chemicals to remove the unprotected material. What I have told, nitric acid or hydrofluoric acid. Those are the two examples of the wet etching chemicals which are used to remove. But in dry etching, gases are used. Like ionized gases are rendered chemically active to generate the plasma actually. Okay, that is used to remove the dry etching. I will explain the dry etching. So So when the interviewer asks you what is etching, etching is a technique to remove it, or it is a process to remove the unprotected material which is not covered under the photoresist material. You have to say this definition. What kind of how many types of etching are there? Dry etching and wet etching, types of etching. Then in what direction how etching is done. Etching can be done in horizontal and vertical, or all in all direction, you can say. This is the part of etching. Now the etching techniques I already told, types of etching, wet etching and dry etching. You have to tell the what is wet etching, what is dry etching. This is much only a interviewer will ask you in the CMOS fabrication. Okay. So in the part of etching only. Okay. Now after this one come the physical structure. What is the physical structure comes here. Like if you see here, this is the basic of the CMOS fabrication. Now comes the physical structure. In the physical structure, you will get to know that NMOS physical structure. What are the things inside a NMOS physical structure? What are things you can see in a NMOS structure? Can anyone tell me? What are the things in NMOS structure? Okay, I already told this in the earlier also. In a NMOS, you will find a P substrate, a N plus two N plus regions, source and drain, one P plus region that is for bulk, one gate oxide that is called SiO2, silicon dioxide, one polysilicon gate. What is a CVD oxide, chemical vapor deposition, that kind of oxide will be there. Okay. Then metal one and a lateral doping effect. If you don't mention the lateral doping effect, that's also fine. But these things you have to mention. Suppose you have been asked by the interviewer, please draw a cross section of a CMOS inverter. Okay. When let me show you. Okay. Let me show you this thing. You have been given a question. Okay. Let me show you. Draw a draw a draw the cross section. It will be draw the cross section of a CMOS inverter. Okay. Then what you will do? What should be your approach? Can anyone tell me what should the approach of drawing a CMOS cross section? All are BTech engineers. You should be knowing this. Hello, please tell. Hello. Hello. Hello, Akila, Ganesh, Nanda. Please tell what should be our approach. Hi, Akila, you are telling something?
What what is the construction process? Are you asking?
Yes, yes. What if this question is given to you in the interview? Draw the cross section of the CMOS inverter. Then how you will approach? You can
Taking
think.
taking P substrate like that only?
Yeah, yeah. You can tell I am drawing that one. You tell. Let me draw it. Okay. Okay. First, what I will take. Hello.
Hello. Taking P
Yeah.
substrate, sir.
P substrate. Wait. Let me take the P. Okay. Okay. Now I have to the P substrate. Okay. P sub. Now what the second?
Um, one side P well and one side
One side
N well,
N
sir.
well, sir. Not P well, it should be N well actually. Okay. P well is a different thing. N well. Okay, already give N well. Okay, now
High, highly
your
doped,
sound is
highly
not coming, Akila.
highly doped P-type material we have to deposit on the
Where we will deposit this one.
anvil.
Okay, that's fine. N well we have drawn that one. With the high doped
In
P-type material we have drawn.
anvil, we have to draw the P-type material, heavily doped P-type material.
P-type material. So for heavily doped, what we will put here? What symbol it should be? It should be P minus or P
Plus
plus or only
P
P?
plus
P plus.
P.
Correct. Correct. P plus. Remember, when it is plus comes, then it is a highly. If it come, it is a lightly doped. When there is no, then it is a like a no doping is there. Okay. Suppose it's for P type, it's a P plus or P minus or N minus N plus everything. When this plus and minus is there, or it is highly doped. High doped. Okay, light dope. Light dope. And it is no doping is there. Okay, you should be remember this one. Interviewer, many interview can point out the if you think it is you can remove it, they can ask you also. Okay, so I'm putting P plus for this one. Okay,
P plus.
P plus for this one. Now
And another N plus and N plus.
this side.
Yes, sir.
Okay, okay, N plus and N plus.
On top of that,
Now
SiO2 is placed.
SiO2 layer is placed on the top of this one.
Total.
Okay, let me put one SiO2. Sorry, let me put one SiO2 layer on top of this one. Wait, let me draw this one. What's happening? Let me sit properly. Okay. Okay. Drawn per. Okay. Drawing is okay. SiO2.
After that, place a photoresist layer.
Photoresist layer. Okay. Done this one also. Okay. This let
And,
SiO2. SiO2 and this was as photoresist. Oh wait. RESIST. Okay. Now
and place the contacts.
contacts how you will show here. No need to put that contacts here. You can just mention that we have to put the contact, but how you will show. Better you have to can tell that we can put the like you have to first
First, we have to diffuse
thing
the
you should be
material
doing.
SiO2 layer.
Yes. You have to tell that SiO2 layer is there on top of this one. Then a photoresist material is given. After that one, no, first your step should be that doping is there, photoresist material is given, then we will create the envelope. First, you should not tell the envelope. You should tell that doping is done in the substrate, photo SiO2 is there, photoresist. Now you will be do the envelope structure drawing here. Okay. Then should be the envelope should come. After the envelope is done, again we will put the photoresist material on top of that one. Again, we will be putting the polysilicon layer. For polysilicon layer, what we will do, we will first let me erase this part. Okay, let me erase this part. This one, what we will do, it will be ending up till here only. Add this part, if you see here, add this part, it is like this kind of structure. In this part, this will, and this should be your gate connection. Okay. In this part also, same if you go here, tell.
Sir, that one is the drain and source. In between both,
Is it okay, Akila? Hello. Hello. Hello.
Hello.
Yeah, tell. Yeah, tell Akila. I can hear you. Hello. Is that
That will be
audible?
the drain, sir.
Drain is this one, na? This is drain.
Okay.
This is source. This is drain. This is source, and this one is gate.
Okay, sir.
Is it okay?
Okay, sir.
See
Okay.
here. If one cross section, I don't know the cross section is there or not. The cross section I can show you. I think is not given here. Okay, so you can see this one: source, gate, drain. Correct. So the middle one is the gate. For both the cases, this should be drain, this should be source, drain and source. Okay, this should be a structure of a CMOS. But one we are missing. Can anyone tell me what is that thing? Something in both the part we are missing.
Bulk.
Yes, who's that one?
Ganesh.
Yeah, good Ganesh. Bulk we are missing. So where we will put the bulk?
The source
P
metal.
substrate.
Got it. We will put the bulk here actually. Okay. At this part, we'll put the bulk here like this. Okay. Let me put the bulk for you. I'll put the bulk here. Let me put the bulk like this, one here and one here. So for now, I have given the bulk. What should be the doping? Now tell me what should be the doping actually here? In PMOS, what should be the bulk doping? Hello. It will be P plus or N plus. The bulk doping in PMOS will be N plus, and this side it will be P plus. Okay. Then we will be able to connect the bulk connection and the bulk connection here. So this is actually the structure of a CMOS cross section of an inverter, which you have to explain in interview you with the process what I have told. First PMOS P sub, in that for P sub what will be there, Scrolowski method we will be doing. So first Scrolowski method, the wave, the invert will be there, that we will cut down. That wafer we will take, we will do some polishing and planarization, smoothness. Then we will build the P substrate by doping. Then on that one we'll put silicon dioxide. Then we will putting on that one photoresist material. Step by step we will making N well. Then we will make the oxide gate, source, drain. Then comes to the metallization. This step you have to tell by drawing this diagram. Okay, so you have to do this. This is the way it should be actually. Okay. Now, so this is the same process only has been explained here. So what are the NMOS physical structure? P substrate, N plus source drain, gate oxide, polysilicon layer, CVD oxide, metal one. So this should be in a NMOS. PMOS also same thing. One extra will be there here is N well, and this will become P plus. Okay. PMOS will also same thing. The NMOS layout representation also, this is the layout representation, this is the schematic representation. Okay, if you see here, source gate drain, here also source gate drain, here also source gate drain. It is built on this style only. Okay, now is this CMOS cross section clear to you? Hello. Hello.
Yes.
Yes, sir.
Okay, See, these are physical structure of PMOS also given. P substrate, N-well bulk. Okay, N-well should be the year P plus source drain, gate oxide, polysilicon layer, CVD oxide, metal one. Same that thing has been explained here. That's a NMOS. This is a PMOS structure. So you should be knowing this kind of structures when you are facing the interview, because this kind of question every time, if you are a fresher, still this question will be asked. If you are going for a director position interview, still this question. This is a very basic question one should be knowing. If the guy is not knowing, then it is assumed that the guy doesn't know anything actually. Okay. Now I will be telling you the sequence, proper sequence. We will teach understanding the sequence only. This in this one I will be telling you the sequence thing actually. Okay. How the step by step you will do it. So fabrication sequence. Step 0, start from here. We will start. I will be putting you a flow chart also. That will be easy for you to understand. Start. For an N-well process, the starting point is a P-type silicon wafer. We generated those from the ingot. The wafer have came, planarization, all things have been done. Then we are taking cutting down, planarization done. Now planarization done. Now after that one, we will do the P substrate wafer. P-type silicon wafer will take a wafer typically 75 to 230 millimeter. I already told earlier also in diameter and less than 1 millimeter thick. This should be the wafer's measurement. You can say 75 to 230 millimeter in diameter, and the thickness should be below 1 mm thick, less than 1 mm thick. Okay. Now we will be doing a epitaxial growth. What is epitaxial growth? A single P-type single crystal film is grown on the surface wafer. A epitaxial, a thin layer is given here. On the surface of the wafer, subjecting the wafer to high temperature and source of dopant material. What is the doping material you are using? And it put in the high temperature. The epi layer is used as the base layer to build the device. This is the base layer actually over the P-type wafer. Okay. So this epitaxial growth is done. Next come the N-well formation. You saw I already earlier told first N-well is done. See here N-well is only done. So this is the mask actually of a N-well, how it looks. Okay. So how it looks actually, this is called a mask. So N-well formation. Now the PMOS transistors are fabricated in N-well regions. In this region only, inside is a PMOS will be fabricated. The first mask defines the N-well region. Okay, first initial step is making the fabrication N-well region. N-well are formed by ion implant. You have to remember, or N-well is formed by ion implantation or deposition and diffusion. You have to tell this thing how N-well is formed. You tell ion implantation or deposition and diffusion. Okay. Lateral diffusion limit the proximity between the structure. Ion implantation results in a shallower well compatible in today's fine line process. You have to tell this difference. That lateral diffusion creates a limit actually. It's make a limit to the, because the proximity angle that should be a 7 degree actually. The angle should be 7 degree of the mask to get an optimal structure. You have, what is the degree of that mask? It should be in aligned to 7 degree angle. It, you have to remember that's a 7 degree angle it should be. So let me write here also 7 degree angle. Okay. 7 degree angle mask. You have to remember, you have to tell the 7 degree angle. The lateral diffusion creates a limit for this one. But in ion implantation, results are shallow, but in today's new kind of structure or fine line structure, ion implantation is only done. Okay. Now then, if you see here, the lateral diffusion done and they have created the structure. They have used lateral diffusion rather in ion implantation. The structure has been created N-well. Now the N-well is done. Active area definition is created. Active areas are created on top of this one. Active masks. What the active region we have in that one? We are creating this one. The active area, planar section of the surface where transistors are built. In this part only the transistor, poly, gate, the polysilicon or the source drain bulk will be drawn. Okay. Define the gate region, the thin oxide, that this is the boundary of the gate actually. In the apart this one you cannot exceed. This should be your boundary. That N implant and P implant, have you seen there? That is this thing only here. Okay. Define the N plus or P plus regions. If you have seen that N plant or P implant, N implant, N implant I think is yellow and P implant was red. If you have remember this guy, okay, in our layout it was, let me do it, N implant, sorry, P implant, and this should be N implant actually. This should be actually one also N implant. In the layout, if you see these two things, you can see in the layout. So if you see N implant, P implant, okay. In this N implant, P implant, a thin layer of SiO2 is grown over the active region and covered with silicon nitride. This on the top of this one, a silicon dioxide is grown on the top of this N implant and P implant. Okay. Up till here, it is cleared how the steps are going actually. Hello. Hello.
Yes, sir.
Up till here, it is cleared.
Yes, sir.
Like, what is the significance of that N implant and P implant now? Okay. Now, in the next step, we will be going and checking what the isolation technique. Okay. The parasitics unwanted fate exists between the unrelated transistor field effect oxide field oxide, that is called, or if it is okay. Source and drain are existing source and drain of the wanted device. Gates are metal and polysilicon interconnects. The threshold of the voltage are FOX fates and higher than normal fates. Okay, so these kinds of some parasitics are there. This kind of isolation technique is done actually in this part. Just to explain, these things are there. Like parasitics, unwanted fates are between the transistor. It's called FOX, like field oxide or the fates. Okay, then the gate metals and polysilicon interconnect. These are the reasons isolation is done, in which parasitic Fox devices, which are called field oxides. Okay. Then in the next step, it come Fox fate threshold is made high by introducing channel stop diffusion that raises the impurity concentration in the substrate in area where transistors are not required. This is done for this particular reason. It is made such a high that where the transistor is not required, the impurity concentration become higher. Okay. This is the reason of the field oxide is being done here. Then what is channel stop implant? The silicon nitride over the inactive region and photoresist over N well as an mask for channel stop implant. That the channel is stopped at this point. That is the reason a channel stop implant is equal to a minus N well mask, like a negative N well mask. It is actually, you don't use this term N well negative. Interviewer might not know this term because this term is very a niche term actually used in the fabrication industry. Many of the guys don't know this negative annual term. Okay, many guys will know, many will not know. Okay, so channel stop mask you can put on the top of this one. After this one done, we can go for the local oxidation. What is local oxidation? Putting the, if you see here, Fox, the field oxide is given here. Now we have to create a trench like structure. We have to cut out like structure. We have to make in this one so that it should get separated. For that one, we use two kind of structures. One is local oxidation on silicon, and one is called STI, shallow trench isolation. Both have different have significance. STI is more used than low cost because low cost have some complexity and limits, like disadvantages, and STI is currently used in today's technologies. Shallow trench isolation. Now come the low cost. What is low cost? A photoresist mask is removed and SiO layer will be act as a mask now. Okay, the silicon dioxide, the thick field oxide is then grown over that one. It's a thick field oxide will be grown that one, the exposing the surface of the wafer to a flow of oxygen rich gas. It will be passed through oxygen rich gas, due to which it will become SiO2, silicon dioxide, okay, or the silicon nitride, or whatever the material they are using on top of this one. The oxide grows in both the vertical and lateral directions. The result in a active and smaller than patterned. So this is the way actually this silicon dioxide is grown over this surface of the P substrate using this low cost technique, in which it is passed through a oxygen gas, due to which this field oxide layer or the SiO2 layer is created on the top of this one. Okay. Then comes your silicon oxidation, how silicon oxidation is obtained by. Is after this passing to oxygen, it is being put in a temperature, high temperature. If you are using wet oxidation, then it should be 900 to 1000 degrees centigrade. If you are using dry oxidation, then it should be pure oxygen, 1200 degrees centigrade. In wet, it is water vapor. So this is the oxidation temperature and oxidation style, wet and dry. That is etching with dry and wet. This is the oxidation, wet oxidation, dry oxidation. It is been put on this one. This is how it will create the silicon dioxide finally. It is put inside through a gas and then put inside a high temperature. Oxidation consumes silicon. The SiO2 has approximately twice the volume of silicon. The FOX is receded below the silicon surface by 0.46 FOX. Okay, so this is the measurement of the total of the overall silicon dioxide on the silicon surface on the wafer. On the wafer, this is the overall of the thickness of the field oxide. You have, if you can omit this one, if that's also fine. You do not need to tell this, but for information you should know this part. But this you have to tell, that it has been passed through the oxygen rich gas, then wet oxidation and dry oxidation is chosen, in which wet oxidation is water vapor 900 to 1000 degrees centigrade, and for dry oxidation is pure oxygen above 1200 centigrade is done there. Okay, till here silicon dioxide thing is created. Now you know how the silicon dioxide is being done. Hello, hello, hello.
Sir,
Yeah, tell.
nothing, sir.
Is it okay?
Okay, sir.
Okay, like up till here, any doubts is there? Look, you see, if you have any doubt, you can ask me. No issue. I am there to help you multiple times.
No, sir.
Oh, Ganesh, Nanda, you
No,
guys,
sir, fine.
is it understood? You can understand these things.
Yes, sir.
Yes, sir.
See, after teaching, you have to read this one. Then only you will get this whole sequence. Otherwise, you will forget. You will forget this one. Okay. So you have to read these PPTs. I will. Is this PPT with you? I have shared to you this one.
Uh,
Hello. I don't think so. I have shared. I will share it to you today. Okay.
I don't think
I
so.
will
We
share
have
this.
it.
No, got it. I don't think they will be having. I will share it to you. Okay. Up till here, any queries are there for you to understand? Okay, then.
No, sir.
Okay. So, can anyone tell me till now today how much we able to what are the topics covered? Like what are the steps? Can you tell me in a brief, someone? What are the steps we covered today? Hello. What are the steps we covered today actually? Can anyone tell Makila? Hi, Akila.
Sir,
Yeah, tell.
fabrication process, sir. CMOS fabrication process.
Like
How the
how? Yeah, tell.
how the taken P well taken N well taken. What are the measurements? What are the etching process? Dry etching or wet etching?
Okay.
These are the things, sir.
Okay. So if any interview comes, will you be able to explain the CMOS process? I will send you the PPT also. Don't worry. You have to read the PPT. And you
Okay, sir.
and I will be showing you that thing also. Okay. I think your interview things will start after the Durga Puja vacation. Okay. So I will be sending you the materials in between. I think it will start roughly in November. Okay. Because the many puja holidays, Diwali, Dashera are there, Chhat Puja is there. After this one, it will be there because many holidays will be there in between. So no HR or things, the process will continue. So it will start roughly in the month of November. Okay.
Okay, sir.
So I will be sending you the materials. Please use those materials in your puja vacation to read and to get the knowledge. Okay. See, once you have the knowledge of the layout and the basics, you are okay to clear the interview. But you are not okay to become a layout engineer. To become a layout engineer, you should be very clear about the like every steps of the in detail physics actually. So that's a different thing. Passing an interview is very easy. You have to just tell the answers 80% to 90% answer. If you can answer, you for that sure you will be selected in the interview. Okay. Okay, then we can end the session here today, and tomorrow again we will meet. So if you have any questions, you can ping me over the WhatsApp. I am available to help you out. Okay. Hello.
Okay, sir.
Okay, sir.
Okay, everyone. Okay, everyone. Okay, guys, you can leave.
Okay, sir.
Yeah, yeah. Hi, Ganesh. Hello, Ganesh. Hello. Hello, Ganesh. Hello, Ganesh.